All right, so last time we began talking about this L2 convergence theorem for Fourier series. So L2 or mean square convergence theorem. And we began discussing some important concepts which are related to this theorem, which show up in the proof and which are kind of very fundamental tools for working with Fourier series. And so right, so what I'm going to do now is just review some of what we did quickly and then proceed with some more discussion about how these different objects relate to the analysis of Fourier series and the convergence of Fourier series. So as I mentioned last time, we're not going to prove the convergence theorem in full detail, but what I will do is outline how the argument works. And so even though we're not going to prove the full thing, a lot of the work we're going to do to build up to the outline later on will be useful for other results, right? It'll be useful for just doing various calculations related to Fourier series. And some of the stuff we're going to talk about we'll actually use to prove pointwise convergence theorems for Fourier series as well. And in that case, we actually will prove the theorems in full detail. Right, and so just to recall, we introduced, last time we introduced inner products, right? And so what is the inner product? And so we're looking at the domain minus pi to pi, just because it makes some of the formula simpler. And so what is the inner product for functions on this domain? Well, you look at the integral of f of x times the conjugate of another function, g of x, right? And so this was defined to be the inner product, which is written as f comma g in parentheses. And so this is like your dot product, right? And so then we had also the L2, what's called the L2 norm or size of a function. And so this is what you get when you take the inner product of a function with itself. And so for this, you should be thinking of dot products and lengths of vectors, and remember that the length or the size of or magnitude of a vector is given by the dot product of the vector with itself, square root, right? And so the same thing is true for this notion of size or magnitude or length of a function, right? So you integrate now the function squared. And so this is the complex absolute value, right? And so this is defined to be we use two bars to distinguish from absolute value, right? Two vertical bars on the left and two vertical bars on the right. And so this is the L2 norm squared. And this arises as taking the dot product or the inner product of f with itself, right? And so in particular, well, what is the L2 norm without the square? It's just the square root of what I have above, right? Right. And so we're discussing the following theorem, which says that if you look at the L2 norm, the size or L2 norm of the difference between the Fourier series of your function at partial sum at size n, the difference of that in your function and this norm, that this goes to 0 as n goes to infinity whenever the function f has finite L2 size. Right? So whenever the L2 norm of f is finite, meaning if you integrate the square of f, then that's finite, right? So this is what we're discussing. And so we ended the lecture last time by proving a version of the Pythagorean theorem for functions, and this turns out to be a key tool in the proof. Right, so last time we saw the following key tool, which is Pythagorean theorem for functions. And so this theorem says the following. So suppose I have two functions and I know that their inner product is 0, right? So that means if I integrate f times the conjugate of g from minus pi to pi, I get 0. The Pythagorean theorem says that if I look at f plus g and I take the norm, the L2 norm of that quantity and square it, that this is equal to the norm of f squared plus the norm of g squared. Whenever you hear me say norm, you can also think magnitude or length or something like that. Like these are all kind of used interchangeably, these words. And also, if you look at the difference, you get the same thing, right? So if I look at the difference of the norm of the distance squared, that this is equal to norm of f squared plus norm of g squared, right? And so a key tool in the proof of this fact is you need the inner product to be 0 in order for this to be true. And remember, this is our notion of orthogonality, right? So this is the same thing as saying that f and g are orthogonal. Orthogonal, again, I've said this a few times now, but it helps to hear it over and over again. Orthogonal is just like a generalization of things being perpendicular, right? Right, and so I didn't mention this at the end of the last lecture, but in the proof of this theorem, we use the following important identity, which it's worth writing out, because you'll be able to use this pretty frequently in types of calculations that show up when working with these objects. So if I look at the inner product of f and g, and I take the complex conjugate of the inner product, well, remember our functions are complex valued, so it's possible that this integral that's used to define the inner product is a complex number, is equal to a complex number. And if I take the conjugate of that, it turns out that this is the same thing as taking the inner product of g with f, right? So it's like switching the roles. And so we use this when we multiplied out this, this norm or this magnitude. We wrote it as the inner product of f plus g with f plus g. And it turns out that one of the 4 terms you get is equal to the conjugate of f and g. Or actually turned out to be the inner product of g with f. And you can write that as we saw doing a calculation that you can write that as the conjugate of the inner product of f and g. And well, if the inner product of f and g is 0, then so is its conjugate, right? And so this is how the proof worked. Right, and I just wanted to point that out because this could be, again, it's a useful identity to remember, which makes some calculations easier. Okay, and now what I want to do is talk about some consequences of the Pythagorean theorem, which turn out to be some like kind of fundamental results in the theory of Fourier series. And then I'm going to outline how the proof of the L2 convergence theorem works without going into too many details, because again, we don't have all the tools we would need to prove it rigorously, so it's not worth spending too much extra time on the argument. Great. So let's look at some consequences of the Pythagorean theorem for Fourier series. Well, what I want to do is let's kind of pretend that, for example, f is equal to its Fourier series, right? We don't know if this is true. Remember, we're writing the coefficients now as the inner product of f with the complex exponentials, right? Where en is e to the inx, right? It's this function. So let's pretend we know that our function is equal to its Fourier series in some sense. Well, what are we trying to understand? We're trying to understand the difference between our function f and the partial sums of this Fourier series from minus n to n. Right? And so we're trying to understand when n goes to infinity, does this go to 0, or maybe the square of it, right? Assuming that we know that our function is actually equal to the series, well, the term that's inside this L2 norm, what would this be equal to? This should be equal to the sum. Well, now I'm only, if f is equal to the series, I'm subtracting everything between minus capital N and positive capital N. So I'm only going to get terms corresponding to n which are larger than capital N in absolute value, f comma en, inner product of f comma en with times en. Well, let's compare to our partial sums. right? So let's compare it to n, the sums from n equals minus n to n, which are the objects we're going to compare to our fixed function f. So notice that, well, these terms here, I'm looking at n in the range minus n to minus capital N to positive capital N. And over here, I'm looking at n, which are outside this range. And so in particular, these terms are orthogonal, right? I mean, right, because all the complex exponentials in the range in the first sum where absolute value of n is bigger than capital N, these values are all distinct from all the values appearing here. And so, well, if each of these terms, complex exponentials, is orthogonal to each of these complex exponentials, we would expect that these two functions should be orthogonal, right? We would expect to have some kind of orthogonality property, but, or not some kind of, we would expect to actually have orthogonality between these two different series. And so in particular, we should be able to use the Pythagorean theorem to obtain some conclusions that relate these two pieces of the series to one another, right? In particular, the partial sum from minus n to n should be orthogonal to all the other terms based on this observation. And so this motivates the next proposition, which confirms this even assuming your function is not equal to its Fourier series, right? So I'm gonna call this a proposition. And so at the end of the day, this really ends up being kind of the crucial identity which makes everything work for L2 convergence. Right. And so the proposition is the following. Let's define, or not define, but sorry, I'm just trying to figure out how I'm going to phrase this. What I'm going to do is define E capital N for error, right? So think error. And so this is going to be the difference between my function f and the partial sums from n equals minus n to capital N, Fourier coefficients times En. And I'm also going to define, just as a shorthand, I'm going to let Sn equal this partial sum. So equal the sum from n equals minus n to n. Right, and so Sn is just my sequence of partial sums for my Fourier series, which I'm trying to show converges in L2. And En is the error or the difference between the partial sums and the function, right? And so we want to show that that the L2 norm of En converges to 0, right? If we could prove this, we would prove the L2 convergence theorem. And Sn is just the partial sum that appears in this difference. And so the proposition is that these two things are orthogonal. So if I take the inner product of Sn with En, that this is equal to 0. Right. And again, this was motivated by the discussion we had before. Like, if we actually knew our function was equal to the Fourier series, then this is maybe a little clearer, because all the terms in Sn are distinct exponentials from the terms in En. And since the exponentials are pairwise orthogonal, well, then this will lead to the fact that, okay, if I take the dot product of this, or the inner product of these two functions, it's going to be some sum of dot products of exponentials. But since each of them are going to be pairwise distinct, all of those inner products will be 0. And so the inner product of the two functions will be 0. It turns out that even if we don't know f is equal to its Fourier series, this is still the case. And so this is the content of the proposition. And so let's prove it. Right, so what we're going to do is just plug in and calculate, right? There's not much else you can do at this point. And so if I look at the inner product of Sn with En, this is equal to 1 over 2 pi times integral from minus pi to pi. I have my function, or my sum Sn, which is sum from n equals minus n to n, inner product of f with En times e to the INX. And then I have the other term, which corresponds to the difference of my function f of x and the same partial sum. What I'm going to do to make the calculations a little bit clearer is I'm going to use different index. So I'll use an m here because we have two different sums which we're going to be multiplying together. So to understand all the manipulations, it helps to make sure that your indices have different labels just to help keep track of everything. Right, so this is En. Right, so the first term here is Sn. This term here is En. And while I'm taking the inner product, so I also need to take the complex conjugate of the second term, right? So this is all with a complex conjugate. So now remember, we can basically distribute the complex conjugates with addition. I'm not sure if I actually mentioned this, but it's something you can check relatively quickly. So if I look at complex conjugate of like z plus w, this is equal to complex conjugate of z plus complex conjugate of w. Right, I think we use this when we prove the Pythagorean theorem. And so what I'm going to do is use this to kind of distribute the complex conjugation among all these different terms. And so now let me do that. So this is equal to 1 over 2 pi integral from minus pi to pi. I have my sum from minus n to n of the first terms, which I'm not doing anything with right now. And now I'm going to distribute all the complex conjugates. So I have f of x bar minus sum from m equals minus n to n of the Fourier coefficients conjugates times e to the minus INX dx. Right, and so here I use the fact that if you look at the conjugate of the Fourier coefficient times e to the INX, this is the same thing as the conjugate of the first term times the conjugate of the second term. But remember, the conjugate of e to the INX is e to the minus INX. Right, so this is what I'm plugging in here. And now finally, what I'm going to do is just multiply everything out. Right, so this looks like a lot of complicated algebra, but we're going to see that all the terms end up being 0. And so at the end of the day, it ends up, despite looking complicated, it ends up being quite simple. And so I end up with now 1 over 2 pi integral from minus pi to pi. Right, so the first term I have is the sum from n equals minus n to n of my Fourier coefficient times e to the INX times f bar. Right, and so this is one term. And then I also have what I get when the two sums hit each other. So I have minus, let me just clear up some space. I have minus now, right? So I have, the first term comes from this series hitting f. And then I also have a term from this series hitting the other series. So I have now sum from n equals minus n to n, and then sum from m equals minus n to n of the product of all the terms, right? So I get f(en), f(en) conjugate, and then I have, oh, sorry, this should have been an m. Right, sorry, I mean, I changed the indice, but I forgot to change in the exponential. I'm sorry about that. Right, so these should all be m's here. Right, so sorry, it's easy to make mistakes like this when there's no audience. Right, and then I have the exponential terms, right? So I have the e to the INX term. Oh, sorry, I'm sorry, I'm mixing up the order of these things. Right, so I have from the partial sum on the left, I have my Fourier coefficient f comma en, and I'm multiplying that by the conjugate of f comma em. And then I have e to the INX times e to the minus IMX dx. Right, and so those are my main terms. And so what I'll do now is split these up a little bit further, and we're going to see that everything will cancel out. So let me break it up into two integrals corresponding to each piece. So the first integral is 1 over 2 pi integral from minus pi to pi. Well, let me bring the sum outside, right? Because remember, an integral of a sum of things is the sum of the integrals. And so the first piece will be 1 over 2 pi, now a sum from n equals minus n to n of integral minus pi to pi of the first Fourier, or the Fourier coefficient, the nth Fourier coefficient times f bar e to the INX dx, right? And then I have the second term, which is the integral of the remaining double sum over here. So minus 1 over 2 pi integral from minus pi to pi of sum from n equals minus n to n, sum from n equals minus n to n of all this stuff. Right? Okay, well I can combine the exponentials, right? So I end up with e to the I. Actually, let me just leave it as it is for, we'll see why in a second. Right, and so let me call the first term we ended up with term A, and let me call the second term we ended up with term B. And what we're going to do is we're going to show that, which is what we need to show, that A minus B is equal to 0. And so it suffices to show that A is equal to B, right? Because then they're going to cancel each other out. Right, and so let's first look at the contribution from term A. So in this case, well, we end up with 1 over 2 pi. Now I have the sum from n equals minus n to n. I have, well, the Fourier coefficient here doesn't depend on x, so I can factor that out, right? So this is Fourier coefficient, the nth Fourier coefficient. And then I have this integral minus pi to pi of conjugate of f times e to the INX dx. Well, what I'm going to do is, well, let me bring in the 1 over 2 pi, right? And so now what I have here looks a lot like an inner product, except the role of the conjugates are reversed, right? And so in particular, this is now the sum from n equals minus n to n of the Fourier coefficient f comma en. And now I have this other inner product where now I have en inner product with f, right? Because I've switched the roles, right? Because the conjugate is on f and not the exponential. So the second term in the inner product is always what the conjugate lands on, right? But remember, we have this identity where you can switch the order in the inner product after adding a complex conjugate, right? So this is the same thing as the sum from n equals minus n to n of inner product of f with en times the conjugate of the inner product of f with en. But remember, if I look at some number z, complex number z, and I multiply it by, and I multiply z by its complex conjugate, this is equal to the complex absolute value squared, right? And so this is exactly what I have here, right? So this sum reduces now to the sum from n equals minus n to n of complex absolute value of the Fourier coefficient squared, right? And so this is what A is equal to. And so now it suffices to show that B is the negative of the sum, right? And so we're going to show that. Right, so what do we end up now if we look at term B? Well, now I have an integral of a double sum. Just like with a single sum, I can switch the order of the integral with the sum and the double sum. And so term B is equal to negative 1 over 2 pi. Then I have the sum from n equals minus n to n, and then the sum also over m in the same range. Integral from minus pi to pi of what's left over. So I have these Fourier coefficients, the en and also the conjugate of the mth Fourier coefficient, and then I have the two exponential terms, e to the inx, e to the minus I mx dx. Well, if you look at these things, well, we're integrating a product of two complex exponentials against one another, and so this should immediately point us towards using the orthogonality of these exponentials. And so, well, let me bring the 1 over 2 pi inside here, which I can because it's a constant, and then we can recognize this as an inner product. And so in particular, b is equal to negative this double sum. Well, I can factor out the two Fourier coefficients because they don't depend on x, right? They're just some constants, possibly complex numbers, but they don't depend on x. And then I have 1 over 2 pi times the integral of e to the ix times e to the minus I mx, which is just the inner product of these two things, right? So now I have the inner product. I'm left with en comma em. Right, and so this is what b simplifies to, but notice that this is 0 unless n is equal to m, right? And it's 1 if n is equal to m, right? And so what this means is, let's suppose we fix n. Right, we have a sum, we're summing over n from minus capital N to positive capital N. Let's just fix one of them. Well, then in the second inner sum, the sum over the m terms, each of these things is going to vanish unless m is equal to n, right? So we're only going to see the piece when m is equal to n. And so this is actually just going to simplify to a single sum. And so this ends up being minus the sum from n equals minus n to n. I have the first two terms, but I'm only seeing the case when m is equal to n, since otherwise everything vanishes, everything is 0. So I end up with this Fourier coefficient, which I just wrote down, and then the second term when m is set equal to n, so I get f comma en conjugate. And then, well, when n is equal to m, the remaining term is just equal to 1, right? So times 1. But this is exactly what we got for a, right? So this ends up being the negative of the sum from n equals minus n to n of the Fourier coefficients squared, right? And so this is minus a. And so this cancels out with term a, right? And so then at the end of the day, we finally get 0 for our inner product, which is what was claimed. Right, and so that's the proof of this proposition, which is kind of like a lengthy algebraic calculation. Hopefully this kind of makes clear the role of like inner products when working with Fourier series. They kind of show up naturally when you do these types of calculations. And okay, this is still kind of a technical result. Like, why is this interesting beyond just like kind of like an aside observation? Well, let's look at some consequence of this result. Right. Well, let's suppose I have my function f of x, right? So I can write my function f of x as a sum of the error term from before and its partial Fourier partial sum, right? So I can write f of x is equal to sum from minus capital N to positive capital N of the Fourier the partial sums for the Fourier series in this range. So I can write it as Sn plus the difference of the two, right? So plus f of x minus the sum from n equals minus n to n of this partial sum, right? And so this was En, right? And so this tells us that, well, f is equal to Sn plus En, but these two functions are orthogonal. And so we can use the Pythagorean theorem, right? And so by the Pythagorean theorem, if I look at the L2 norm of f squared, well, this is the same thing using this identity as L2 norm of Sn plus En squared. well, since these functions are orthogonal, we can use the Pythagorean theorem, which now says that this is equal to norm of Sn squared plus norm of En squared, right? And so if I plug in, what do we end up with? So we get, well, therefore, the L2 norm of my function f squared is equal to the L2 norm of the partial sums up to point n of my Fourier series squared, plus the L2 norm of the error term. Right. And well, we're trying to show that this is zero, converges to zero. Right. 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 And so, well, what I want to do now is just calculate what this is equal to. Of course, we're not going to be able to use this identity to prove that the error term converges to zero, but we're going to be able to deduce from this identity a very important theorem in studying Fourier series. So I want to illustrate this now. Right. So let's calculate this particular norm. Right. So this is equal to by definition, this is 1 over 2 pi integral from minus pi to pi of this sum times its conjugate. And since I'm looking at a product of two sums, once again, I'm going to change the indices. So m equals minus n to n of f comma em. Well, we have to take the conjugate of everything. So I get conjugate of this coefficient, and then e to the minus I mx dx. Right. This is just plugging in the definitions and using the properties of the complex conjugate as we did in the previous calculation. And so, right, so let me multiply everything out as we did before. If we follow the same kind of algebraic manipulations, I get now a sum over n, a sum over m, 1 over 2 pi times integral of the product of all the terms of each respective term. So I get fen, the mth times the nth coefficient times e to the inx times e to the minus imx dx. This is the same term that we ended up with up here, right? This is just this term. And so, except for the minus sign, right? We have a positive sign now rather than a minus sign. And so, well, we showed that this term using orthogonality is just equal to the sum of the squares of the Fourier coefficients. And so this is equal to, using the same argument that we did in the proof before, this is sum from minus n to n of the Fourier coefficients, absolute value squared. Right, and so I can plug this into the identity we have up here. And so this implies now the L2 norm of my function is equal to the sum of the Fourier coefficients from minus n to n squared, and then plus the error term, the L2 norm of the error term. Right, so this is like f minus the partial sum. Right. And so in particular, we obtain the following theorem, which is called Bessel's inequality, which is, okay, let's suppose I look at the formula above. Notice that this sum plus the error term is equal to the L2 norm of f. Well, the term on the right is always bigger than or equal to the sum of these, this sum, right? So this sum always has to be less than or equal to the L2 norm of f. And so the theorem is the following. If I look at the sum from n equals minus n to n of my Fourier coefficients squared, that this is less than or equal to the L2 norm of f, 1 over 2 pi integral minus pi to pi, complex absolute value of f squared, right? This just follows from the fact that, well, again, this term is bigger than or equal to the sum, right? So these terms are just bigger than or equal to one. Like if you have a sum of two positive numbers, it's always bigger than or equal to one of the two, right? Right, and so this is a direct consequence. Well, notice that here's the kind of big conclusion. The right-hand side is independent of n, of capital N. And so I can, on the left-hand side, I have something that does depend on n, but this is true for all n, right? Since the right-hand side of the inequality doesn't depend on n, and the left-hand side is true for any n, we can take the limit and let n goes to infinity. And so this tells us that if I look at the sum from n equals minus infinity to infinity of my Fourier coefficients, right? So I look at the sum of all the Fourier coefficients squared. This always has to be less than or equal to the L2 norm of the function squared. Right, and so this is like actually what Bessel's inequality is usually called. And so this tells you that if your function f is square integrable, meaning the integral of f squared is finite, then the Fourier coefficients always have to be summable in this way, right? So the sum of the Fourier coefficients squared is always finite, right? And so this is true even if the function is not equal to its Fourier series necessarily. All we're using here is a less than or equal to, right? And so there's another piece of information, though, which we can obtain if we further assume that, well, what happens if we know we have the L2 convergence? If we know we have the L2 convergence, then that means that this En term, which is the length of this difference, or the L2 length of this difference, is converging to zero. So if we had this is converging to zero, then we wouldn't have an inequality. We would actually have an equality here. And this would tell us that the L2 norm is equal to the sum of the squares of the Fourier coefficients, which we can also deduce from this identity. And so I'm going to write this as a second theorem. And so this is known as the Parseval's theorem. Right, and so this is the following. So suppose we know that we have the L2 convergence result, right, which we haven't proved yet. But suppose that f minus the partial sums from minus n to n of the Fourier series converges to zero, right? So this is saying suppose the L2 convergence theorem is true. Then the consequence, which is really just, again, the Pythagorean theorem, is that the L2 norm of the function has to be equal to the sum of the Fourier coefficients squared from minus infinity to infinity. And so this is a very important theorem in mathematics. It has applications all over the place. And so, right, and so what's the proof? Right, so from before, we had L2 norm of f squared is equal to sum from minus n to n of the Fourier coefficients times squared, sorry. Plus the error term squared, right? But the L2 convergence theorem implies that this converges to zero as n goes to infinity. And as n goes to infinity, this is going to converge to the sum from minus infinity to infinity of the coefficient squared. This is just the definition of what it means for an infinite sum, right? And so this is the proof. right? And so notice, well, I mean, I'll do an example later on where we do a calculation that uses this fact, but notice this tells you that both of these are either both finite or both infinite for one, and also that you can calculate the values of this infinite series by just calculating an integral of one function. And on the other hand, you can also calculate the value of the integral of one function by looking at the value of this infinite series, right? So these two objects are the same, right? This is what the theorem tells us. Okay, and so, right, so what I'm going to do shortly is now outline how to actually show that these en terms converge to zero without going through all the details again, because we need some technical tools which are not available to us in this class to fully rigorously prove the theorem. The first thing I want to do, though, is briefly pause and discuss a more general version of Bessel's inequality, which we're actually going to use when we talk about pointwise convergence of Fourier series. And then we'll go back and complete the outline of the proof. So let's briefly talk about a more general Bessel's inequality. And so in this case, we're going to suppose that we're given some functions xn, capital Xn, which are functions on the interval minus pi to pi. And we're going to suppose that they're orthogonal and in fact orthonormal. So n is just an integer. And so we're going to suppose that xn, if I look at the inner product of xn and xm, that this is 1 if n equals m and 0 if n does not equal m, right? And so these are just like the complex exponentials, but maybe they could be other functions. So for example, we could take xn to be some constant times sine of nx. Right, remember we had an orthogonality property for the sine functions, right? Or maybe some constant times cosine of nx, right? So why do we need these constants here? Well, just so that this term is 1, right? If this term is not 1, you can always divide your functions by this term in order to normalize it so that it's equal to 1. I mean, the key point is really the fact that the inner product is 0 unless n is equal to m. Right, and so the theorem is the following. And so this is what's normally called the more general Bessel inequality. And so it's just like the conclusion we had up here for the Bessel inequality for Fourier coefficients, except now you're not going to have the Fourier coefficients here, you'll have something slightly different. And so the theorem is that if you look at the sum from n equals minus infinity to infinity of the inner product of f with xn squared, right? So these are not the Fourier coefficients. There's some other, maybe more generalized Fourier coefficients for a different set of functions. This is always less than or equal to the L2 norm of f squared, right? The L2 norm of f squared, right? And this is true for any system of orthogonal functions or orthonormal functions in this manner, right? Defined in this manner. For example, the sine functions or the cosine functions, right? And so, for example, this is true for like sine Fourier series and cosine Fourier series. Everything we've been doing up until this point has been complex exponential Fourier series. This Bessel inequality also says that the same thing is true for sine and cosine Fourier series. That's one example. And it's really going to work for any orthogonal collection of functions. And so how do you prove this? Well, if we let, let's call S tilde n be the partial sums, not the Fourier series partial sums, but the partial sums you get by combining these orthogonal functions, right? So the same argument that we did before shows that if I look at Sn tilde, that this is orthogonal to f minus Sn tilde. And so this is like our error term, modified error term. And so using the same argument, you can show that if I look at the L2 norm of f squared, well, this is the L2 norm of f minus Sn tilde plus Sn tilde. And so I have a sum of two orthogonal functions. And so by the Pythagorean theorem, I get the sum of these two squares. And then so in particular, this is bigger than or equal to, let me throw away the first term, it's bigger than or equal to the L2 norm of Sn tilde squared. But you can calculate using orthogonality right, using this orthogonality assumption for the xn by following virtually the same argument we did with the complex exponentials, but just for these more general functions, you can show that this is equal to the sum from n equals minus n to n of these coefficients squared. Right. And then what you're going to do is let n go to infinity, and that's the proof. Right, and so this is typically, again, when you hear Bessel's inequality, it's more generally used in this manner. And so as I mentioned before, we're actually going to use this version of the theorem when we talk about pointwise convergence of Fourier series via kind of a clever argument that brings orthogonality back into play, even for pointwise convergence. Okay, and so now to end the discussion for related to the L2 convergence theorem, I just wanted to outline a proof of how it actually works. Oh, sorry. Right, so let's outline the rest of the proof of the L2 convergence theorem. Right. And so the idea is basically that if you consider among all classes of possible combinations of trigonometric functions which approximate your function, it turns out that the Fourier series is the best approximation. And so using this observation, you can obtain the convergence result. And so let me go through this. So there's two main points. The first is related to approximation by trigonometric polynomials. Right. And so what is a trigonometric polynomial? This is like some combination of cosine terms and sine terms, just like our Fourier cosine and sine terms, except that these coefficients need not be Fourier coefficients, right? They could just be, they may not be the Fourier coefficients for the function, right? They could just be anything. Right. And so why are we thinking of these as polynomials? Well, I mean, you could think of it as like powers of cosine, like say an tilde to the power of n. But by Euler's identity, right, you can relate powers of cosines and sines to just cosine of like nx and cosine of sine x and so on. Right? And so there's a theorem from a branch that's known as real analysis. which says that, well, any function, right? So suppose we have a function which is square integrable, right? So say on minus pi to pi. There's a theorem from real analysis that says we can always find a trigonometric polynomial that's arbitrarily close to the function in terms of the L2 distance, right? So then for any capital N, we can find a trig polynomial P with, if I look at the L2 difference of F minus P, that this is always smaller than 1 over N, right? And so as N gets very large, this means that I have a bunch of trigonometric polynomials which are getting very close to my function in this sense. So the problem is, well, you may think, well, isn't this what we're trying to prove, right? The issue is that we don't know that these polynomials have anything to do with the Fourier series, right? So in particular, the coefficients may not be the Fourier coefficients for F. So this doesn't imply that the Fourier series will converge, right? This is just some other polynomial, and we're not. It's not. I mean, it's not. Right. The polynomials could wildly vary depending on the choice of N, right? It's not like it's the same sequence of partial sums. We really have no real information about what these polynomials look like, right? So we know there's some sequence, but it may not be the sequence of partial sums for the Fourier series, and so this is not enough to imply the full result. So how do we get from this result to the L2 convergence result? And so this is something that's usually called the least squares property of Fourier series, right? And so, well, this theorem up here tells you that there's some trigonometric polynomial that will approximate your function. What the least squares property tells you is that the Fourier series is always the best of the polynomials to approximate your function. And it tells you so in a quantitative way that allows you to actually conclude from this fact that the Fourier series will converge to the function. Right, and so the least squares property is the following. So suppose P is a trigonometric polynomial. Well, using the de Moivre identities, we can write P as a sum from, like, say, n equals minus n to n of some coefficient an times e to the inx. And again, the big issue is, as a warning, this may not be the Fourier coefficients. Right, so even though this combination is very close to the function, this could be very different from the Fourier series as we want it to look. And in particular, the coefficients could change for each n, right? So to be more precise, I should actually index them also by capital N. So for each capital N, maybe the coefficients change, right? So this is the big problem. But the point is that the least squares property tells you that if you look at the approximation between F and its Fourier series, right? So this is the Fourier series, the partial sum. If I look at this difference squared, that this is always less than or equal to the difference from any other trigonometric polynomial, right? And so an are arbitrary, right? And so this is true for any choice of an. So this tells you then that among all possible combinations of these complex exponentials, which we want to use to approximate our function, the best choice of the coefficient to get the best approximation is always the Fourier coefficient, right? So it doesn't matter what you put here, that you're always going to have a better approximation if you use Fourier coefficients. That's what this inequality tells you. And so the proof of this, which I'm not going to do in full detail, so the proof is it's very similar to the argument we did like 20 minutes ago. So you show a certain orthogonality between the different terms. And in particular, what you do is you write f minus the trigonometric polynomial. Well, I can write this as f minus my Fourier series partial sums plus the remainder. Oh, I spelled that wrong. Right. And then you show that these are orthogonal. And so you can use the Pythagorean theorem to get this inequality as we did before. And so this is a calculation that everyone here can do if you are get used to working with inner products. I'm just going to omit it because it takes up a bit of time. And since we're not fully proving the L2 convergence theorem anyway, I think the time is better spent on some other topics. But the point is that this inequality, you can prove it. Once you realize that you have this decomposition, you show that this term, which is like the error between the function and its Fourier series approximation, is orthogonal to this other remainder term, which is a calculation you have to do. Well, then you use the Pythagorean theorem, and this inequality follows almost at once from the Pythagorean theorem, right? And so then the idea is, well, how does the proof of the convergence theorem work? Well, from point 1 here, we have this result from real analysis, which tells us that if I fix n, I can find a particular trigonometric polynomial such that the L2 distance between my function and that polynomial is less than 1 over n. And so this polynomial will be of the form I have here. And in particular, the different coefficients may not be consistent with one another. Like they could vary a lot depending on the choice of capital N. But I know that there's some polynomial I can plug in here that's very close. But then using the least squares approximation property, I know that the difference between my function and the partial sums of the Fourier series is always less than or equal to whatever that was. And so in particular, it's always going to be less than 1 over n, right? But now here, the term we have here is independent of the polynomial, right? This is just a number. And so now I let n go to infinity, and that gives you the convergence result. Again, unfortunately, it's contingent on this kind of independent result from real analysis. So I do want to point out, though, that if we were more focused on just completely developing the theory of Fourier series in full detail, which we're not doing in this class, we're only spending like maybe 3 weeks on the theory. But for example, if you took a whole class devoted to Fourier series, there's another way to prove this actually using Fourier series in a clever way, which is related to a different type of convergence, which we're not talking about here, right? So you can prove this theorem kind of directly without appealing to like fancier theorems from real analysis or something like that. You can prove this directly using a certain variation on Fourier series, which unfortunately we don't have time to talk about in this class. And so actually the natural logic is to maybe more talk about this kind of variation on convergence, which is not discussed in our textbook, and use it to prove this theorem. And then you can prove the L2 convergence in full detail. But we're again kind of skipping over that for now. Okay, and so from now on, though, that's an overview of how the proof would work, and we've talked about a lot of the important ideas that show up in the proof, and a lot of the important tools that show up in the proof. And so from now on, we'll assume that the theorem is proved. Wait. Even though I didn't completely prove it. And so in particular, well, let's go back here we're going to assume that we have this the Parseval theorem, which tells us that, well, we're assuming that the partial sums of our Fourier series converge in L2 to the function. And so in particular, that tells us that the L2 norm of the function has to be equal to the sum of the squares of the Fourier coefficients. And so let's do an example that illustrates how this is kind of sometimes helpful for calculations. And then we'll be done for the day. Right, so let's study the function f of x is equal to x on minus pi to pi, right? And so let's check to make sure that our function is equal to the Fourier series in the L2 sense. Well, let's calculate the integral of the function squared. Right, if I take absolute value of x squared, it's just of f squared, it's just x squared, right? And so this is equal to 1 over 2 pi. Well, now I take the antiderivative, which is x cubed over 3, and I evaluate that at the boundary points minus pi and pi. And so this is 1 over 2 pi times pi cubed over 3 minus negative pi cubed over 3, which is plus pi cubed over 3. And so I have 2 pi cubed over 3. And so this ends up being 2 pi cubed over 3 times 2 pi times 1 over 2 pi. The 2 pi will cancel with 2 pi on the bottom, so I end up with pi squared over 3. Right? And in particular, of course, pi squared over 3 is finite. And so this tells us then that the, right, so x is, so this says the L2 norm of x squared is equal to pi squared over 3, which is of course finite. And so the Fourier series of f of x equals x converges in the L2 sense. Right, and so let's actually try to calculate what are the Fourier coefficients for this function. I mean, I think we actually did similar calculations for the function in previous lectures, but I don't think we did the complex Fourier coefficients. So let's just do these quickly. Right, so I'm going to let Cn be the nth Fourier coefficient. So this is 1 over 2 pi, integral from minus pi to pi of x times e to the minus nx dx. Well, let's evaluate this these integrals. We're going to have to integrate by parts. Let's first consider the n equals 0 case. Well, in the n equals 0 case, I have 1 over 2 pi integral from minus pi to pi of x dx. But x is an odd function, and we're integrating it between minus pi and pi, right? So we have something that looks like this. Well, these two regions have the same area with different signs, and they're going to cancel out when we evaluate the integral. So this is just 0, right? And so now let's assume that n is not equal to 0. And now to evaluate, we're actually going to have to integrate by parts. Well, what I'm going to do is just let me move the 2 pi over to clear up some of the notation. And then 2 pi times Cn is equal to integral from minus pi to pi, x times e to the minus nx dx. Let's integrate by parts. And so my x will be like the u, and this will be the dv. Well, du is equal to 1, and v is equal to minus 1 over in e to the minus inx. And so this ends up equaling for the boundary terms, I have minus 1 over in x e to the minus inx evaluated at the points, boundary points minus pi and pi. And then I have minus the integral of, well, du, which is 1 times v, right? I get plus because the minus signs will cancel, 1 over in integral from minus pi to pi of e to the minus inx dx. Well, as we've seen a few times by now, this last term will vanish, right? And if you don't remember why, just pause the lecture and do the integral. It's not too hard to check that this integral is 0. And so we end up just with the boundary terms from the integration by parts. And so I end up with minus 1 over in, and then I have pi times e to the minus in pi minus negative pi times e to the in pi. Right? The two minus signs cancel, so I end up with summing these two together, or sorry, I end up with a positive pi, which I can factor out. So I get minus pi over in, and then I have e to the in pi plus e to the minus in pi. Right? But remember, we had these de Moivre formulas, which relate complex exponentials to trig functions. And in particular, if you look at e to the I theta plus e to the minus I theta, we saw that this is equal to 2 times cosine of theta. Right, so let me plug in cosine here. And so I end up with time minus pi over in times 2 cosine of n theta, or n pi, excuse me, nx, n pi. Sorry, I'm all over the place right now. All right, so 2 times the cosine of n pi. Well, cosine of n pi is either plus or minus 1, right? So this is equal to minus pi over in times 2 times, in particular, cosine of n pi. Well, it's equal to 1 if n is even and minus 1 if n is odd. So one way of writing this is just minus 1 to the n, right? And so these are my Fourier coefficients scaled by 2 pi. And so finally, if I divide by 2 pi, right, we had 2 pi Cn was equal to this. So therefore, Cn is equal to minus 1 over in times minus 1 to the n, right? And so if I look at absolute value of Cn squared, this is just, excuse me, this is just equal to 1 over n squared, right? Okay, and so now let's use the Parseval theorem. Right, so we calculated the L2 norm of our function f, which is the function x, right? And so f squared is x squared. And we saw this is equal to pi squared over 3. And then we also just calculated each of the Fourier series, or each of the Fourier coefficients. And for this function, we know that from the L2 convergence theorem that the Fourier series will converge in the L2 sense. And moreover, we have the Parseval theorem, which recall says that if I look at the L2 norm squared of my function, that this is the sum of the Fourier coefficients squared from minus infinity to infinity. And so for this particular function, well, we calculated the L2 norm of my function was pi squared over 3, right? And so this is equal to now the sum of the Fourier coefficients, the Cn squared. Well, remember, if n was equal to 0, we just got 0. And so this is actually sum from minus infinity to infinity when n is not equal to 0. And for each of these terms, we saw that Cn squared is just 1 over n squared, right? But notice that if I have negative values of n and I square them, the minus sign goes away, right? So for example, minus 1 and 1 contribute the same, minus 2 and 2 contribute the same, minus 3 and 3 contribute the same, and so on. And so this is actually just equal to twice the sum from n equals 1 to infinity of 1 over n squared. And so the Parseval theorem tells us that these two terms are equal. And so therefore, we conclude that if I look at the sum from n equals 1 to infinity of 1 over n squared, this is equal to pi squared over 6. And so this is kind of like I guess, a famous identity. And so notice we use the whole theory of Fourier series in order to prove this, right? the only way we know these two are equal is by using this very fancy theorem about L2 convergence of Fourier series. And here's a simple application to calculate a certain infinite series, right? Okay, and so next week we're going to turn to, I think we'll spend maybe 1 to 1.5 more lectures talking about convergence of Fourier series. And so the main topic will be pointwise convergence results. And so for these results, we're actually going to prove them in full detail. And so we'll have a whole class of functions where we'll know that the Fourier series will converge actually pointwise and uniformly to these functions. Great, so thanks.